So we're going to start the panel discussion by having about a two-minute introduction from each of the panelists, and then we'll talk about how neurotechnology is looking like in research, in clinical practice, and in the industry, and what are the difficulties that they're facing, what can we do to progress this field. So if we can have Yannick start off, it'll be great. We can just go around the panel.
Yeah, sure. Hi, my name is Yannick Roy. I'm one of the co-founders of NeurotechX. I'm obsessed with neurotechnology. I'm currently doing my PhD at the University of Montreal, extending my PhD by doing not research during the weekend and the week, focusing a lot on NeurotechX, scaling this international community. So we started in Montreal in 2015, and I started just out of passion, wanted to bring neurotech enthusiasts together from research, hackers, DIY, a bunch of people who were watching videos on YouTube. There was no Facebook announcement, no Elon Musk announcement. There was just people who were excited about BCI, brain simulation, and different advancements in the field. And we started getting people together. And as we, first event, second event, and more, and some other cities around the world, we're starting reaching out and saying that it's pretty cool that in Montreal we had a neurotech ecosystem, neurotech community, and we're like, we did it. We kind of made it. Mm-hmm. So we saw that pattern there that other city could benefit as well from having kind of a local community, kind of a bottom-up organization as opposed to having kind of a top-down approach to neurotech, and just passion-driven to see what is missing in the ecosystem, what people want. In Montreal, it happens that we wanted to get together to learn more about who's doing what kind of project can we work on, and things like that. And NeurotechX grew. We had New York and San Francisco joining as next city, and then Toronto, and now we have 20 cities around the world. And then we started student clubs because we had a lot of undergrads coming to different events, and they were like, it would be nice so that we can work on projects, but it was hard to start a student club because there was no competition, there was no kind of like league of neurotech stuff. So we kind of like put the whole framework. We started some student club. We have Sayan here from Neurotech UFT. So we started student club at McGill with ETS in Montreal and the University of Toronto, and we created an international competition as the first model in 2015. And then last year we had a second edition, was online because we want to increase the reach so that people can join this competition. So they were working different challenges in neurotech, and be happy to talk more about that. But yeah, just out of passion, and then we have Neurotech Hamilton doing this hackathon. So we're really excited to see a lot of people coming to different events and talking about different challenges, whether it's from ethics, data, deep learning, more consumer facing, more research, and now we're going to have also a discussion about more clinical settings. So very exciting time in neurotechnology. I'm excited to be in it.
Thank you, Yannick.
Thanks, Saurabh. So I'm Sue Becker. I'm a professor at McMaster in the Department of Psychology, Neuroscience, and Behaviour. I've been there for 25 years, and my lab is called the Neurotechnology and Neuroplasticity Lab, and we're reflecting the broad range of things we do, but all around an interest in how brains work. So some of the work is experimental, some of it involves computational models of the brain, and some of it involves applications like neurofeedback and brain-computer interfacing. Some of the applications that we have worked on a few years ago with some colleagues, I developed a novel algorithm for hearing aids based on computational models. So a model-based hearing aid that we called the neurocompensator, and a startup in Hamilton actually adopted the technology. Another former PhD student worked with me and Ian Bruce on a computational model of auditory cortex that led to a model-based treatment for tinnitus. And he's actually got his own company now and has commercialized that, so that's pretty exciting. And then some of my former and current PhD students are working on different EEG-based technologies for developing applications. So I'll let Kiret speak to that.
That's a good segue. So my name is Kiret. I did my PhD with Sue Becker on brain-computer interfacing. Right now I'm a postdoc in the Department of Surgery, and I split my time between McMaster and the Becker Institute. So I do more deep learning on medical imaging right now for medical decision making, but also some stuff in neurofeedback data modeling in EEG and trying to get deep learning to work in EEG, but I don't think it works very well right now. A lot of my work has been on ways of getting BCI out of the laboratory, in the sense that to get there, we need to personalize systems so that there's not this one-size-fits-all solution that we kind of have now. And that means generalizing the machine learning approach that we use in brain-computer interfacing so that different people can use different kinds of control signals depending on what works for them personally. And I'll leave it at that for now.
I'm Graeme Moffat. I'm the Chief Scientist and Head of Regulatory Affairs for InteraXon. We make Muse, which I think is the world's best-selling EEG system. I built a model based on all of the modeling I learned from Sue as a graduate student at McMaster on EEG sales in the world, and I think we sell more EEG systems now in Muse. Now, granted, it's a very inexpensive EEG system than all other systems combined, and that technology comes from scientists and engineers from Toronto and scientists from Hamilton. So I guess you could say that one of my goals professionally is to have the Hamilton neuroscience and neurotechnology community take over the entire world of neurotech. And we're competing actively with the Montreal neurotech.
Over there soon.
That's why you guys are sitting on different sides. So I'm Jordon Charlebois. I'm a medical doctor here in Hamilton. My area of specialty is psychiatry, but my professional interests lean a lot into neurology and neuropsychiatry. I work occasionally at the brain injury clinic and a lot of the inpatient units with people kind of all over the spectrum with like psychiatric and neurological disorders. So I'm here mainly to speak as a clinician. But I met Saurabh through some of our mutual, we call them attendings, mutual staff who we work with. We're involved in some projects related to fMRI, and I've also done a little bit of work with researchers who are using right now EEG. So those are my interests.
I'm Asa Ansel. I'm a clinical neuropsychologist. I'm half-time at the General Hospital, which has a Neuroscience Awards. And I've known Graeme for a few years. I called him at one point to see if I could find out more about the Muse. My particular interest is operant conditioning of the EEG, and that's also known as neurofeedback. I'm interested in looking at some treatment effects of the operant conditioning. We started a randomized controlled trial study at the hospital of individuals with traumatic brain injury, comparing people over a period of at least 10 to 15 sessions of training, at least 5 days a week. I need to have a little army of students in order to do that because it's very time consuming. Not that each individual session is time consuming, they only take 20 minutes, but we have to coordinate schedules. It gets complicated. And so we're looking at comparing people who are getting the neurofeedback training, people with traumatic brain injury, to another group, and they're randomly assigned to the groups, basically one and then the other. Another group that's doing some training in working memory using some computer software training of working memory, both visual and auditory. And eventually we'll have a large enough data set to be able to maybe make a comparison. Our goal is to get, I think it's 139 in order to have at least a decent chance of detecting a difference if there is a difference. It's going to take some time to get there, but we're not in a hurry. So as a clinician, I see lots of different people at the hospital, individuals with acquired brain injury, strokes, learning disabilities, and actually I can see the benefit of, or I've read about the benefit of using operant conditioning or EEG biofeedback and other forms of biofeedback, heart rate variability training, for example, to help with hyperarousal for people with depression, anxiety, PTSD, or individuals with learning disability. There's that whole literature on ADHD, and maybe looking to see if it helps with attention training in individuals with traumatic brain injury in comparison to a different way of training their attention. I want to be able to drill down to see, what are some of the assumptions, whether they're actually supported by looking at the data carefully. For example, one of the protocols is to inhibit theta in order to improve attention. Well, I don't know, when you inhibit theta, does that mean you have an effect on beta and alpha as well, maybe delta? So one of the students this year is going to do a very careful analysis of the training in an individual over consecutive days to see what happens. It's all very interesting, and it's all very new because very few people who actually do this type of training, even commercially, actually do research in the area. So I'm glad to see you all. I'm very happy to be here.
Thank you very much. That's actually a great segue into my first question about what's the underlying neurophysiology behind these neurofeedback protocols and neurotechnology. It seems like that is what this kind of field is gravitating towards, at least in terms of clinical applications and administrative applications with neurofeedback. So what's the underlying neuroscience behind it, and what's the research behind which one's better, alpha, beta, or is there a difference between them? The one on the research side,
Sure.
Can you comment on that?
So, yeah, in neurofeedback, especially in clinical neurofeedback, there's a lot of work on upregulating or downregulating alpha or beta or theta-beta ratios and all these things. I think ultimately these are meant to get at underlying networks of brain regions, although they don't do it, I think, very well, from my personal opinion, or from the research that I've done. One example I think that's very interesting is in PTSD, there's evidence that both upregulating alpha and downregulating alpha at the same location are both effective, which from a neuroscience standpoint doesn't really make much sense.
From a science standpoint.
From a science standpoint, it doesn't really make much sense. So I think what's really happening is that there's some activity that's being picked up, possibly from the salience network or the executive control network, so networks that control or that are impaired, you could say, in PTSD, and that any kind of control or operant conditioning of that signal or of those networks is useful, because probably what's impaired is the connection or the communication between those two networks, or even between nodes within those networks. So any operant conditioning will help boost connectivity within those nodes, so that you might get some benefit out of it. So I think what I'm trying to say really is that we have these kind of surface level correlates of brain activity that we're interested in that are being targeted in neurofeedback, when really we need to look at what's underlying that specific brain activity. So what is the network that's impaired in a certain disorder, down to what kind of subtype of this disorder does this individual have, and how is maybe this individual's brain activity impaired with respect to some normative measure of brain activity, and what should we be targeting neurally for that specific patient. But that's not what we're doing now.
Add to that? That makes a lot of sense. And another sneaking suspicion I have, given that things like both upregulation of alpha and downregulation of alpha are equally effective, or both are effective, it makes me wonder if it isn't just that you're learning this general cognitive skill, you're learning a cognitive control over your brain state. And upregulation of alpha should put you into a more relaxed state based on what we know about alpha. Downregulation of alpha should put you into a more attentive, focused state, perhaps. But maybe it doesn't matter which one you do, you're just learning to have a good control over your brain state. And if you do that it'll generalize. It's a general skill to be able to suddenly go relaxed or go attentional focus or any number of other states. So it could be that's just a generally good skill, and maybe it almost doesn't matter which signal you go after. I don't know. That's a hypothesis that should be explored as a possible explanation, because we don't know what you're really training when you're using these measures.
And I think what Sue is getting at is essentially mindfulness is what we're training in people. And I don't have as much experience with the nitty-gritty of differentiating between different frequencies in my clinical practice, but I do have some experience with neurobiofeedback and head injury, and then therapy in general, like actual talk therapy, which acts at a much higher level of abstraction, even though it's impacting neurological networks. And the thing that I worry about in this frontier is that we'll commit the same kind of sin that we did in psychiatry, a necessary sin of setting up our categories like we did with the DSM, and kind of creating these relative, they're not arbitrary boxes between, alpha and beta and theta. Like, we agree that there are some commonalities that we can discern between different people, but I think what's much more relevant on a functional and a clinical level is what is happening, like maybe one level of abstraction above this. So whether or not the alpha channel is going up or down, are we able to learn to modulate our attention or our arousal? And I think we're at risk because EEG is very objective, or it appears very objective because you're looking at a quantifiable measure. We're at risk of kind of overselling it, and I think the big thing is that we're really just training people how to use their brains. That's the one thing we can be sure of.
Yes, I'd like to add something that's very interesting. I mean, I don't know if you've read any of Ottmer's work, OTHMER. In the field of neurofeedback, Ottmer wrote about the fact, this thing that you talked about, how maybe it doesn't really matter what we train people to do, that it's the act of training that is helpful for them. So it doesn't matter if we get them to upregulate beta or downregulate theta, or upregulate alpha or downregulate it, that people are benefiting simply from the exercise of learning to make those changes, to have an effect on the balance of the different frequencies. So there are a lot of assumptions out there, and I agree that it's important to look at the networks, because I mean the information from the networks, the data from the salience network, we've known about this for, I don't know, at least 10 years. How many years has it been since people have been writing about the salience network? So it makes sense to try and associate it with various networks of the brain. I mean, it requires more technology. You can't determine that with a few electrodes. You need to have probably gene 64. Is that how many?
32, maybe 64.
32?
Yeah.
So it makes it a little more difficult. I mean, I have a system, but I purchased it myself, and because I had an interest in it and wanted to get into it. It wasn't cheap, but it's not. How many channels? I think it's like a 19 or 21 channel, and then you include everything. Can I figure out what's happening with the salience network with that many channels?
To some degree. I mean, there are spatial filtering techniques and things like beamforming that would be very useful to use, but you don't really see that in the literature right now in neurofeedback. Right? There's a lot of just quickly. There's a lot of things that have been developed in biomedical engineering and EEG signal processing that we use in brain-computer interfacing that I never see in the neurofeedback literature, unfortunately. And I think neurofeedback needs to move in that direction.
And actually, the work that Saurabh is doing, maybe you want to talk about it, because that's very relevant, right?
That is very relevant to this work. So what we're trying to do is trying to identify EEG markers for these networks, salience network being one of them. And to that end, actually, I wanted to add that one of the major nodes of the salience is is anterior insula, which is pretty much out here. So you don't even need that many electrodes to get to signals that are above it. What the other electrodes add is ability to distinguish between salience and other networks, such as the scintillating network or the default mode network. So if just salience network is enough to provide you with a little more clinical insight, it should be fairly easy to, I shouldn't say fairly easy, it could be plausible to look at a low electrode channel system that's localized around this area and kind of go forward with that. The salience network is primarily focused in two areas, with this anterior insula being one and the anterior cingulate cortex, which is typically the center of the brain, which none of the EEG systems can get at properly. But yeah, that's really good, interesting discussion. Maybe that brings it to Graeme, where given that the salience network, which is it's quite superficial compared to the other the nodes and some other networks, do you think this is something that the Muse could be able to potentially pull out?
Yeah, I mean, I think the how we advance signal processing in how Muse uses these signals for direct feedback is there are a lot of promising, I think a lot more promising avenues even than just a few years ago because of the development of advanced tools. And one of the great advantages of being closely tied to McMaster and to the University of Toronto and to these sort of very top-end neuroscience institutes is that we get to see the tools long before they permeate the neurofeedback community. I told the story earlier today of how we failed to build a BCI, an active control BCI with Muse, and that was what Chris was originally trying to do when he made this interface for Steve Mann's wearable computer thing. What he did by accident, and what actually became Muse, was he was trying very hard with this EEG system to make something happen by thinking. And then he finally figured out that by thinking this and not thinking that, it was literally just grasping his attention and focusing on his breathing and then unfocusing and doing that and getting very good at that. He accidentally taught himself mindfulness meditation. So that was the failure. This is one of these classic technology pivots. We thought we were building this, and it turned out we were building that. We had tried to build a brain-machine interface for controlling a mouse cursor, and ended up with a mindfulness learning tool. So that's a useful thing, and it may be more useful than a thing to control a mouse cursor badly. And just the very concept of being able to move an EEG signal through whatever it was, and you could do that approach a number of ways. You could do it based on targeted frequency bands. You could do it on the basis of a naive machine learning classifier. What Chris did was he just forced himself to do this, and he finally figured it out. And in going through the process of that, he achieved metacognition. And so that's sort of one of the essential elements. You recognize that you are not your thoughts, and that you can choose to think this versus that, which is exactly the same thing that CBT does, cognitive behavior therapy. You are not your thoughts. You don't have to feel these things. You can cognitively control your emotional response. So that's a very, very powerful tool. And I think that is, we're really just scratching the surface of that. The other thing that's exciting about, as Kiret I think is right, that the neurofeedback community is 30 years behind the times, but some of the tools that I talked about earlier today and that we've been talking about in some of the workshops are going to completely change the way that we do signal processing in EEG, and that we think about signal and noise and background, and as this becomes more widespread. I hope it doesn't become too widespread too fast, because I want to put it in Muse before anyone else does. Before anyone else does it for their system. But once these things become more widespread and more easily usable and accessible, I think that really will be a game changer for the use of EEG in diagnostic and therapeutic interventions.
You talked about making this really widespread, and I think this is a good point for Yannick to comment on. Because looking at the growth of NeurotechX, again, 3 or 4 years ago, and now you're globally in 16 or 17 cities, that's an exponential growth of neurotech enthusiasts. How could neurotechnology or NeurotechX play a role in this kind of growth of neurotech and maybe help advance this field as much faster rate.
Well, by different means, I think that one example is like here in Hackathon, and Graeme mentioned it earlier. I think that it's going to happen, and the field will continue to grow. Now the question is how, and it's going to be more prime time. What are we going to see in 5 years, 10 years, or 20 years from now? And I think that by just engaging more people that are interested, or at least give them a chance to try to learn more about it from a technical background. So, for example, like. People just trying to discovering the Muse, for example, in a hackathon and being like, oh, that's interesting. I didn't really considering going in a neuro journey. I'm just an electrical engineer, for example. That was kind of like my thought when I started my undergrad. I was like, I'm just an electrical engineer, but I would like to work with the brain and do like neurotech stuff. And I didn't know where to start. I was like, what can I do? I'm just an electrical engineer with some computer science background. So I think that this is where a community like NeurotechX, you have some different kind of events. You have an online community, so you get exposed more and more, and then you develop some skills, you contribute to discussion, you meet some people, and at the end of the day, you might enjoy, or you might just leave and do something else, like in AI, and be like, oh, there's more money in AI than VR, or cryptocurrency, or whatever. But at the end of the day, just giving a platform to try and develop some skills, some interest, and just test it, I think that there's a lot of value in that. So this is one aspect. Then just developing skills and having a network so that you can, for example, like start a company, start a venture, and just exchanging ideas and providing these events where you have a lot of collision from different backgrounds, researcher, and then someone from industry, and then someone with some skills, and then you bring these people together, and they're like, oh, let's just try. And then I think that these little things can definitely play a big role when you look back. 10 years from now, we look back in time and be like, yeah, this definitely contributed. It's hard to assess the impact that NeurotechX can have right now looking forward, but I think we like to sometimes compare ourselves with the Homebrew Computer Club in the Silicon Valley, where Steve Jobs, Wozniak, and other people were going, and just kind of like out of passion because they like playing with electronics and building computers and things like that when it was not a thing yet. And now looking 10 years later, looking back, it makes sense that they have impacted the field a lot, and they've helped creating the Silicon Valley. So we're kind of like hoping to achieve that kind of things where 10 years from now. And we're already seeing some startups emerging, a lot of people getting some jobs, for example, at InteraXon and others, and kind of like seeing all the little impact, but obviously many years from now we'll have this ripple effect over time. So that's more on the impact. Another thing that we're really passionate and engaged is more the ethical aspect and all the culture of neurotechnology in general, about accessibility, open source, open access, privacy of data, all these things that are not skills but more culture and discussion. So engaging and having kind of like growing in that culture of talking about it, because it's not necessarily something when the field is prime time and when you're like, okay, we need to have some rules and engage. I think that it starts way before the field is actually prime time to just grow in this culture, and then when in 15 years from now these things are kind of like embedded because we've grown with these values. So we talk about open source more and more, sharing data sets, sharing data, things like that. So I think that this is kind of like a side effect of a community like that just talk about it again and again.
Those are great points. To kind of add to that, the reasons behind me finding Hector and starting at Neurotech Hamilton was my interest in neurotechnology. So I actually grew up in the Middle East, halfway around the world, where they're actually eating breakfast right now. I wanted to study the brain. I knew I had that interest, but I also like designing things, and I like engineering. So I was trying to pick a university program. I kind of settled on electronic engineering, electrical engineering, whatever. But then I saw in McMaster they had this program, electrical and biomedical engineering. I said, hey, the brain's an electrical system and biomedical engineering, why not? Maybe I'll learn about the brain then. Got here, I am having such a hard time finding people who work with brains. I'm working in a medical imaging lab, and I'm doing random stuff, and then Kiret walks in one day, and I just happened to be the guy who was running this. And I'm just talking to him, what kind of research he does, and he said, brain-computer interfacing. I said, that's what I wanted to do. Where do you do this work? In psychology, neuroscience, behavior. What? I don't know why would that person do that work there, but that made perfect sense when they got there. And so she's my PhD supervisor now, Becker. So this is by chance and by fluke I kind of ended up here, and I'm sure there's people out there who are interested in this, and they just haven't had that chance, and they don't know where to go to meet these people who do this kind of work, and that's why I think having this platform where people can come to and know who to contact, know where to go, and learn more about this would be very helpful in helping advance this.
The same thing happened to me.
Oh yeah.
I did my undergrad in physics at McMaster, and I got, I started out in physics, and then I thought, hey, these images of the brain over here look cool. What's that program? Oh, that's medical physics. And then you start to solve the problems of image correction in MRI, and that's pretty interesting. But it's not as interesting as what the actual images are.
Right.
And it turns out that the brain research is the interesting part.
Exactly.
So you sort of gradually find your way into it. Mine was I went to there used to be a bar on campus called the Downstairs John. It was a Meet the Profs night. And Larry Roberts, who became my master's supervisor, was there, and he explained neuroplasticity to me. And I said, I'm going to go do that. EEG. And that turned into neurotechnology. So these serendipitous things that we were very lucky to sort of cotton on to now I think can happen intentionally through organizations like NeurotechX.
Right,
Fund this more easily.
Yeah, hopefully these hackathons can help do that. I'm sure some people here are also hoping to kind of take an idea and see how can we convert that into maybe a startup, because that is another thing that can really inject money, inject public hype into some of this work, and also help advance the field. So maybe Graeme can comment a bit on that as to what is it that the business front, I'm sure you have to deal with your CEOs and people who want to make money.
Yeah, it turns out that businesses have to make money or they don't last.
Right. So what do they look for in sort of a technical product like this?
Well, I think it's a real challenge. There are a lot of neurotechnology startups, and the ones that keep going have a product that finds a niche that works. In the case of Muse, we gave people a reason to put EEG on their heads, and so the market, to a certain degree, was already existed. People who wanted to learn how to meditate and struggled to do so because it's a hard thing to learn. And if you can make it a little bit easier through, most people who want to learn how to meditate, and it's becoming more and more popular to practice mindfulness. It's kind of where yoga was 15 years ago. So it's getting a lot bigger. There's a brain gym in Yorkville and Toronto that teaches mindfulness, and they have all kinds of technologies to support it. So when we found our niche, it was in a pre-existing market that there was a market need there. And I think we've answered that to a degree, and there's still potential to grow. But ultimately, you have to solve a problem, and you have to solve a problem in a way that someone will pay you to do it. If you don't do that, and part of the reason that, or part of the discipline, I think, of making a sustainable technology that scales is having an interaction with the marketplace as early as possible, and testing and iterating, and figuring out whether you've got the right fit. We call it product market fit, or if you don't, adapting quickly enough that you don't go out of business before you find the product market fit. It's a very different challenge than science and engineering. In a sense, it's an engineering challenge, but it's a very different challenge, and not everybody can make that transition, which is why so many great companies founded by really good engineers with good technology run out of time to make the technology work. So that's a delicate balance, and often the most successful companies, like you think about Apple, Wozniak was the guy who really understood computers, and Steve Jobs was a businessman and figured out the magic of how to sell and how to make products work for people. And often the most successful startups, and I think that'll be true in neurotechnology as well, will be a mix of different skill sets. It's very rare to find those skill sets in the same individual. And scientists and engineers tend to want to solve the hard technical problems, make things work really, really well. I tend to try to hold things back from going out into the product, maybe more so than the marketing and product teams would like at Muse. And they say, listen, we've got to get this out the door. It doesn't work perfectly yet. That's okay. You can send things out the door, and then you can fix them and iterate them in software after the fact, which is another new thing thanks to mobile technology and app-based and cloud-based tech. But,
If I may add, that's at the treatment end, right? Getting people to use mindfulness and different things.
Yeah.
There's the whole diagnostic question.
Oh,
Whether
yeah.
technology can be used for diagnosis and looking at different networks and how there's all kinds of literature on how the different networks are differentially activated in different types of psychiatric conditions and brain injuries and strokes. But the thing is that if you're going to commercialize this, if you're going to sell it, you need norms, right? You can't do it without norms. It's like, I'm a neuropsychologist.
In a medical device context.
Exactly.
Yeah, you need standards and norms.
You need norms. So as a neuropsychologist, when I give a test and the test is standardized, I need to be able to know whether that's normal. And so to get norms, you have to have a certain sample size, you have to screen your subjects, you have to show reliability. That's not cheap, right? I don't know what kind of sample size you need. Maybe you need like 50, 60 per decade age group or something. I don't know until you get the right. You can look at split half reliabilities or test-retest reliabilities and figure it out how many people you need. But that's where a lot of the money is actually, because if you don't have the norms, then from a diagnostic perspective, it's not going to stand alone. And I know in my field in neuropsychology, assessments are moving towards more objective quantified measures. That's the latest thing. So I have my little system of 21 channels, and I can do my QEEG. But I bought access to a large database, commercially available database. So with a discriminant function, and I mean it's not great. I mean I think they do have there is some software in there that breaks it down into various networks, but it's older technology. This data is from the 1980s.
Is that for?
Yeah, Thatcher's. And it's thousands of dollars, but I mean, there really isn't anything comparable right now, especially not in Canada. If we had a normative database, I would just buy the Canadian software.
There's the other challenge is that there are regulatory constraints on some of these technologies. So the only things that you can use EEG for clinically in the diagnostic sense, besides epilepsy, which is classically used for 90 years, is for as a diagnostic aid in attention deficit disorder and for medication dosage correction in depression. So there's two companies doing this, both in the United States. They're FDA approved and they're reimbursed services. But I think as you rightly point out, the better we get at these norms, the better we get at data, the more useful this technology becomes. And this isn't true not just of EEG, but of FNIRS, of MRI is getting very good at this, anatomical and functional. So there's real potential here for a lot of innovation.
Absolutely.
And
So
it's not going to be us, it's going to be these guys.
yes, but we do have to collaborate. Like the university has to collaborate with the hospital, and because we have the patients, right? We have all the ABI, stroke, you name it, we have it. And there are lots of neuropsychologists, clinicians. So we do have to collaborate more, I think. That would be, that's a given, I think. But I mean, strictly speaking, you don't need to look at those individuals for a normative database. But can you collect data, normative data, outside of the structure of the university? As a company, can you go out and say, okay, I'm going to collect data, and I'm going to make sure everybody's screened and collect data on, 600 people? Is that too expensive for a company to do?
I can't speak to the price, but having peripherally been involved in some attempts at this, just using data like video conferencing data, so just like mirror communication for the purpose of facilitating CBT, I know that it becomes exponentially more expensive as soon as you fall into the market of a health product, because there's additional security measures that you have to take in terms of like levels of encryption, because it's personal health data that you're now dealing with. Muse probably doesn't have to do that because they're playing with mindfulness, but if we're labeling it,
we have to be very careful about what we say and what's on the box and what's in the endorsements, because as soon as you use certain words, that changes the category of the product.
Yes. Yes, it does.
In line with that, and speaking to what Graeme was saying about kind of uncoupling, kind of personalizing somebody's ability to explore mindfulness. There's a huge, and also in the context of companies that need to make money and need to kind of make themselves sustainable. There are one of the most expensive things for the province, actually the most expensive thing for the entire province, is the healthcare budget. So it's over 40%, and that's just the Ministry of Health. And a humongous component of that is things that could be personalized further. So for example, in Hamilton, we're spoiled, I find. Like, I've worked in this industry in Windsor, London, Toronto, Thunder Bay, and I think we're actually spoiled in Hamilton in terms of our access to mental health resources, but it's still 6 to 12 months for me to get certain types of tests on people, 1 to 2 years to get certain types of therapy for people, and the kind of expertise needed to do those therapies is not that high. And so if we could kind of, in the same way that Muse makes mindfulness more accessible, if we could do it for something like CBT or operant conditioning, like for ADHD, like if somebody could find a way to scale that in a reliable way that we could recommend as providers. Like, I send people to like websites all the time in hope that they can, at least this can hold them over until they can see like a professional therapist. I send people to all kinds of stuff like that.
That's coming. That's definitely coming. So there are companies, mostly in the U.S., who are now getting certified CBT apps, like Pair Therapeutics. These things are going to be standard in 2 or 3 years, and they'll be for specific indications and specific kinds of CBT delivered gamified through apps.
And that would save us, like, just from that perspective, forget about helping people and like the amount of life that would be saved and the amount of suffering that would be treated. That would actually like save, like from a bottom line perspective, that would save the province and the taxpayers and everybody else millions and millions of dollars, which is ultimately the incentive that keeps these things around.
Definitely, that's a really good point. I'm going to take a small break at this point and move to the audience. If they have any questions that they would like to ask. Yes.
I actually have kind of a random question, but we were just hearing about the depression and like the psychological therapies. I was just wondering if any of you or your respective institutions have any interest in the effect of psychedelics and the brain using EEGs and such. The reason being, my background is actually biopharmaceutical sciences, and then I actually got a greater interest in technology, hence like the year. I've only been learning coding for like a month and a half. I'm just trying to get my foot in the door. But the reason being is that even from a business standpoint, the antidepressant industry is actually a multi-billion-dollar industry. And there's new clinical research, 2016 research published in Nature and several other papers that one strong dose of psilocybin, which is the active ingredient in magic mushrooms, actually cured depression for 6 months in patients that were terminally depressed, terminal cancer patients that were severely anxious and depressed, so they're about to die. One strong dose cured them of depression for 6 months. The study was 6 months long. This is a billion-dollar industry, so that there is a return on investment. I was wondering if any of your institutions are actually researching that, because currently antidepressants aren't even curing people; they're treating people. And some there are.
That some of the time.
I was just about to add to that. I did a paper on that, and there's several papers that actually suggest that they're marginally better than placebo. So there's a natural compound that actually can cure these things, and also results in neurogenesis. If we studied the effect of these psychedelics using the EEG, could we stimulate the same parts of the brain to recreate that experience, I guess, promote neurogenesis and therefore cure people? Is there any active research in this department in any of your institutions? And what are your thoughts? And
So yes. So the 5-minute spiel on the topic I'd be happy to spend like a week talking about is it seems like the disruption of the dysfunction of the default mode network, so the midline cortical structures that we see with slightly over time with antidepressants, more acutely with psychedelics and electroconvulsive therapy, it seems like that's associated with, it seems like it's the DMN, which is the focal point of the treatment kind of effect of these interventions. We're doing a study right now at the Anxiety Treatment Research Center, ATRC at Westfit, using MDMA in PTSD, individuals with PTSD, which isn't quite a psychedelic. We also use ketamine in research capacity for people with major depression, and I know my wife's hospital in Joseph Brand uses it as well. So those are the two that we're using right now. There were 2 trials on psilocybin in the last 2 years that looked at end-stage cancer patients, I think it was.
Yeah, I think it was like 50 patients.
And it was around 50% treatment efficacy. In the endpoint was approaching death with equanimity, which is like a pretty awesome thing, which SSRIs don't do, which antidepressants don't do. So the short answer is yes, the research is happening, and I think maybe for one of the first times, like the medical industry is on the right side of this. Like usually you see like, you know, the medical industry is the like, you don't like change, like stick to the old guard kind of stuff. And it's actually, I think, doctors and people working in hospitals who are like, these drugs suck, we would love anything that works. And it's a regulatory issue and a political issue that keeps us from moving faster on this. The second part of the question is the relevance of EEG in this. And it doesn't, it might be relevant in terms of kind of characterizing things like I was talking about, like with the default mode network, and more of like pathophysiological understanding. I don't know off the top of my head if it would be as relevant from like a treatment perspective, because that's something that we can more subjectively and clinically see. So if somebody just says, actually I feel great, and I'm like approaching death from a perspective of peace, I don't really care what their default mode network says about that. Like they're happy, and that's more what we're focused on at this point.
She had another question on top of that for Graeme. Oh, we're continuing with that one.
Can I touch on this topic before you go to another question? So I can't speak to the impact of psychedelics, but I'm very interested in kind of complementary approaches to treating mood disorders. And one of the studies we're running now is comparing the impact of aerobic exercise versus using the Muse sort of neurofeedback mindfulness versus the combination. And running is well established in rodents, and there's some indirect evidence in humans that does upregulate neurogenesis and has very well established antidepressant effects. And in rodents has a neuroprotective effect against stress, so you're less likely to create a depressed rodent model if the animal is exercising and has healthy levels of neurogenesis. So neurogenesis is really interesting in a lot of ways, but it may be that boosting neurogenesis has a bit of an antidepressant or neuroprotective effect. And I would predict that the Muse neurofeedback / mindfulness would act more sort of by a top-down mechanisms, training maybe your salients or executive networks that are cognitive control, whereas the running would exert more direct effects on the hippocampus and maybe over stress regulation, and that they might be very complementary and act on different pathways. So our prediction is that the two combined should really synergize, and we're looking at undergrads who are not a clinical population, but nonetheless about 30%, as many of you will know, are very, very high on stress and depression. They have sleep deprivation, they have a lot of pressures, a lot of our students are working multiple part-time jobs and so on, and there's a lot of mental health issues in that population. So I study healthy populations, but we see impact of running on mood in our past studies, and there is room to improve their stress and depression levels, and so this study will be interesting in terms of looking at that synergy.
And I think Saurabh's research, the fMRI data, is essentially, if I could cram millions of dollars worth of research into a sentence, is like chronic stress shrinks your medial hippocampus, shrinks all of the regions of the brain associated with neurogenesis, and so probably the relief of chronic stress is associated with more neurogenesis, which has a bottom-up effect on things like depression. So I think it's a pretty, I don't think like that there's a lot of speculation in that. Like, I think it's a
Yeah,
Can you
exactly.
hold it off?
Yeah, I can. Definitely.
Thank you very much. Let's give someone else a chance to ask. Hector?
I have a question. So, you were mentioning about a possible collaboration with, Dr. James, with researchers and with Graeme, with InteraXon, and with academia. So, my question is, how would this collaboration look like? Like, what we want to do with Neurotech Hamilton is really be at the center of this triad, right? Like the business people, the clinicians, and the research. So, my question is, when I tell you like collaboration between all of this, what's the first thing that comes to mind? Like, what would be a low-hanging fruit project that we can start doing like next week, like metaphorically speaking?
Right, I mean, there's so many possibilities. We could, if the technology and the resources were available, we could start looking at the different networks and how they might change with certain types of neurofeedback. That's what I'm interested in, although the exercise research sounds really fascinating too. Collaborating in that way to see if to see what is happening when we're doing training, whether it is sort of hitting on one or two networks that we could access easily, say with the anterior insula. And if we were able to do that in an effective way, we might be able to come up with some sort of very clear-cut and marketable approach to helping people with attentional disorders or even hyperarousal. Hyperarousal is a big problem in people too because they have trouble calming down their nervous system to a level where it's optimal for things like sleep or maybe optimal for things like studying to be able to regulate that. You can do that during using mindfulness too, but I think that you might be able to do it faster using neurofeedback.
That's really interesting.
I might say something even more practical than that is, for example, ASA often would reach out and say, hey, I'm having a technical issue with the Muse, and with the study that we're doing, we need this auxiliary electrode to work like this, and it doesn't work like that, or the connector isn't working. And because we're in Toronto, I can't just come over and debug. But Neurotech Hamilton would have enough expertise here that we could have. It's these informal networks of technical expertise that often potentiate breakthroughs to problems in research and engineering. We moderate an online forum for people developing on Muse, and we still do. But most of the questions now go through the NeurotechX Slack. Most of the technical questions related to working with Muse, developing on Muse, building on neurotechnology on other platforms. NeurotechX Slack has sort of become the default go-to for questions about EEG data, about new techniques, about hardware, what works, what doesn't. And so when somebody comes to me, I often get an email in my inbox that says, hey, I want to do this with the Muse. Can you help me out? And I say, sure, I'd love to. I don't have time. Go ask that same question in the NeurotechX Slack, and I will flag it up for somebody to answer.
That's really interesting because this community has kind of taken over this workload that.
And it could only work as a community, right? We have to crowdsource this because Muse isn't big enough to handle all of the inbound requests for information that we get. And we would be answering the same question over and over if we weren't able to just point to, here's the answer over here, or here's a forum where that question has been asked for something very similar, and here's the network of expertise that you can draw upon.
That's an excellent question. I struggled for months last summer trying to figure out how I could cheaply, do an FFT. Somebody that I knew, Sid Segalowitz, who probably were here for Brock, suggested, well, why don't you look at Excel? So he said, Google it. He said, I found something. There's some instructions. You can do FFT on Excel. And I thought, really, that's awesome. So I did it. I just followed the instructions and I was able to do it. But if I had somebody around that I could ask, maybe we could have, somebody could have, helped me with their access to other ways that we could get this FFT to look at the data that's coming down from the Muse and to look at the different aspects of the data that I wanted to.
I might know someone writing some introductory scripts for EEG that might be of interest for you. So
I would love to hear about it.
absolutely.
So to add to that, we have bi-weekly hack nights where we invite the neurotech community or people who are interested in learning about this or have problems like yourself to come in and talk to us, and some of us are present there and help other people who are there want to work on these projects. So that would be a really good way to get clinical populations or clinicians who are trying to get into this field in on this and help resolve some technical issues. Maybe it'll help with the study more structured form. Maybe Yannick can comment on this, where how would we incorporate more clinical branch in NeurotechX and allow them to integrate with the already huge industry partnerships we've developed with Behaviour.
Yeah, well, it's definitely not an AC necessarily. It's because, as Graeme said, it works with a community, but the more people at some point, people need to converge. So Slack is a very good platform where people can come. So the first answer would be, for example, like Slack would have definitely would have found people that would definitely help for that in seconds, for sure. Because these are common things, and so someone live would have answered that. So I think that one way where NeurotechX can help is through different channels, for example Slack, but also, as you point out, with hack nights, with different events. So maybe I would say extending our reach more to the clinical sector, because we have a good reach in different universities, for example, grad, undergrad, but maybe less in the clinical sector. So maybe that's a way of, because these events are there, as you mentioned, hack nights and things like that, but that has probably not reached your practice, for example. So I think that it's more of a matter of reach, maybe.
Reach and connecting to people who might be interested in this.
Yeah, exactly. And also kind of like informing and trying. It's trial and error. Like NeurotechX is all about bottom up and trying to see what people need. So, for example, as I said earlier, the student club was we had undergrads coming and saying, hey, it would be nice to have that in the university. So we kind of like listen, and now if we start having a lot of requests that voice the same, then we're like, okay, let's see what we can do with that. So with that spirit, it's kind of the same thing. It's just like, let's try something. As Graeme said earlier, let's pivot. Let's try it. Does it work? Doesn't work? Not really. Then move on and try other things. But that's kind of like the spirit of NeurotechX. I would say expanding the reach and proposing and asking maybe like challenge night, I don't know, where people can kind of like, these are my problems. Can someone help that? And then you also have, obviously when it's a clinical or research, it's less of a problem, but when there's a business, it's also always kind of like, am I doing like free stuff for a business? That has a bit of friction when there's kind of like, this is my challenge, but I'm a business, and I'm asking people to do it for free. So that obviously has some friction, but that would be interesting for example, from a clinical setting where I have some problem with an electrode or some FFT or anything. Here's my challenge. Can someone help? A lot of people will be willing to definitely help with that.
I would say it's also a track territory for clinical sector as well, right? Because clinician can just share the data with you that you can help them analyze them in some way. And on the flip side, you might provide some scripts that already work on the data to help them with something. How do they credit you properly? How do they incorporate your work and your contribution into their picture? This is something that we have to really think about. And related to that, very close to what we're talking about, there are all these labs and clinics that have really good data sets. We all have our small data sets, but we don't really have a mechanism for us to pool our data sets. Day-to-day population. I think that's a big shift. That's maybe one route a corporation can take to fill a gap in that, but there are regulatory issues as well that we think are potential reasons.
So we, a bunch of NeurotechX people at the Society for Neuroscience meeting a week and a half ago went out for a beer and happened to run into the president of the Canadian Association for Neuroscience. And he said, hey, have you guys heard of the Canadian Brain Research Strategy? And it turns out this is a big initiative around coordinating brain research at the federal, provincial levels, university levels. And what they said was, the goal is to partly try to solve that problem, which is also the Ontario Brain Institute tries to solve that problem. But they're super, super keen to bring in organizations like NeurotechX and private sector actors like Muse. So so that we can all work together as a country and try to create this future industry, which we think, I think this is I think neurotechnology is realistically a thing that could be a very, very big and important industry for the future of mental and brain health. And I think it's something that Canada can create a lot of jobs for a lot of scientists and engineers and a lot of people, and create real wealth for our country, while we're also doing good for the world. One of the things that there's a quite a famous neuroscientist, who was the discoverer of spike time independent plasticity, who has gotten up and said in every forum that he can, we need things like neuromodulation and neurotechnology to work for mental health, because we literally can't wait any longer for better therapies. To your point, the drugs that we have for the central nervous system don't work very well. And one of the things that's gotten pharma very excited in the last few years is something they refer to as a drug-device combination. So a neurostimulator plus a drug that acts on the central nervous system. So you use the pharmaceutical to alter neuroplasticity in some way, change receptive fields, and then you use stimulation to drive changes in network connectivity. And this is, vagal nerve stimulation is an example of this, which is modulated by central nervous system pharma. So you can, these things potentially have more powerful outcomes, or more useful outcomes than drugs alone or devices alone. So, heart rate variability, like these are not, one, the magic bullet idea, like a single pill to solve the problem, is not going to work for the brain. It's too complex.
Yeah, and the diagnostic categories are not based on the brain. I mean, they're based on symptom constellations. I mean, it would be like diagnosing heart problems just on the basis of symptoms. They don't do that. They look at the structure, they look at the function of it. And I mean, that's where we are, unfortunately, with the diagnosis of schizophrenia and different things. But it would be nice if we could base our treatments on the basis of what the networks are doing.
We have time for just one more question. Yes.
More from some from the outside, I'm trying to look in. What is really being sensed in the difference between something like a low-end sensor for a brain scan to a significantly higher? Like, are we looking at microvolts sort of signals, or is it like a voltage sort of sensor issue? Is it, what is that you're actually seeing between, let's say, $1 million brain scanner versus what we're dealing with here with the Muses, or with different levels of equipment?
So I'll answer, and I'll give it to the panel to fill in the gaps. What I think is, in any imaging modality, sensor modality, you're always trading something for something else. So you have to make a choice as to what you want to measure, how much money you're willing to spend on the measurement or the equipment, how portable you need it to be, whether it has to sit, an MRI needs a building, a special building, any kind of radiological imaging platform needs special walls, and MEG needs nickel. So that's very, very expensive, and it's like what we're doing. EEG is considerably less constrained, even the high density systems, but you're still very expensive. You can't move them around very easily. I remember there was an idea at McMaster to build a truck with an EEG system that was going to drive around to different hospitals and do research. I don't know if that ever came to fruition. It may no longer be necessary because we now have a dry sensor system with a much lower cost and much more portable. But dry sensor systems and low-cost systems are noisier. I think the one advantage that we have now is that because consumer electronics, largely because of the smartphone and computer industries, have gotten so good and so cheap, you can get very linear amplifiers, you can get great ADCs, you can get electronic components necessary to build these things have come down in price by 3 or 4 orders of magnitude in the last 10 years. And that's mostly due to the smartphone industry. So we can buy these things off the shelf, put them into mobile brain imaging and sensor and stimulator systems, and they perform as well as the highest grade research systems did in the same channel orientation as they did 10 years ago. So the quality of the systems has gone up while the cost has come down for sparse and wearable systems. So the trade-off is not as bad as it once was. It's still a trade-off. It's always going to be a trade-off. The same is true of MRI. So MRI now, Western just installed, University in Western Ontario is installing a 9 Tesla scanner. The magnetic field of this thing is monstrous. You need a room around this thing so big where you can't even carry any metallic things into it. But at the same time, Synaptive in Toronto is making half Tesla scanners that have a highly uniform field. A field that you can put on a trolley and wheel into an operating room, put over a patient's head, and wheel back out. And those are going to cost much less money and they're going to be much more portable. You're not going to get the same resolution, but the question is, if you have an idea of what resolution you need to make it a practical and useful thing, that offers enough information to decide on what you can be able to make applications from there.
I guess at a high level, there are 2 ways to look at it. One way is what's the best system I can afford, and what can I do with that system? And the other way is here's what I need to do, and what system can I do? If we focus in on EEG a little bit more, I think the biggest differences between various systems are going to be the number of channels or electrodes we have, and the configuration of those electrodes. Muse, the individual channels are not that bad, especially with the configurations of electrodes. But you have 4 channels, so the question is, what can we do with these 4 channels? And there are a lot of things that you can do. You have to be creative. If you had basically the same hardware, let's say 25 or 26 channels, there's a lot more you can do with that. It's a much more expensive system. I think that's a lot of the trade-off is really in terms of the density.
I think getting to what I was saying like at the beginning about overemphasizing the kind of molecular biology or the electrophysiology. So, like, individual neurons are firing signals that exist on the order of magnitude of millivolts, but you're measuring like collections of them kind of pulling together through the cerebrospinal fluid. But why is it important to be measuring a single neuron? So you have to think about at what level of abstraction is the thing that I care about. So is it something like generally being able to pay attention and respond to a cue, which you can do from just 4 channels or something like that. And even though you might not have deep knowledge into like the functioning of this individual's brain, all you care about is that level of abstraction, which is like the general task of paying attention to something. And that's what I think we need to worry about more. Yeah, I think the other point. So the level of abstraction is important. And then also I think like it's incredibly valuable doing things like this because the simplicity of it like really constrains us and forces creative solutions and innovation. And so if we all had 9 Tesla MRIs in buildings that would like suck up burst and the walls weren't thick enough, we would be a lot lazier and a lot less creative. But if we were forcing people to do things with a minimal number of electrodes and less spatial resolution, it actually like leads to, I think, more innovation and more understanding because you're constraining the process.
Well, you're not only constraining the process, you're also opening up the possibility that your breadth of applications becomes much larger because you can take this anywhere. And they're ubiquitous and it costs $179. So that makes them much more accessible.
Yeah, I want to add onto this that fMRI is great if you want to pinpoint, roughly where in the brain the activity is coming from, but it's really lousy at timing. And if you want to study, what frequency is the brain oscillating at, and what's the pattern like Graeme was showing us some cool results just before we came in about alpha actually happening in bursts. And you could not study that in fMRI. So EEG gives us the temporal resolution, and there are so many more things we could do with it if we knew what to look for. There's so, we've just scratched the surface in terms of understanding how whole networks of neurons operate together and their dynamics, and that they're resonating in different frequency channels. And in the memory literature, people are starting to look at things like theta gamma coupling across brain regions. If we can start to get a handle on those more interesting dynamical features, brain in across time, which I think is where we need to go.
There is some, I mean, is Loretta, I mean, it has a specificity of, I think, about, is it half a centimeter or 1 centimeter cubed? Loretta, so, what is it, low resolution, what is it? It triangulates. Yeah.
Basically tries to find in 3 dimensions where the activity comes from.
And, yeah, and it has the resolution, I think, of about almost like a little less than 1 centimeter cubed.
Yeah, so you're not going to be doing that with Muse because you need a few more
No,
channels.
yeah. But there is technology available for localizing. It's just not at the millimeter level. So, I mean, if we don't need the millimeter level, and we don't, because we know that the EEG arises from large numbers of what they call pyramidal cortical neurons in the cortex, and it's basically EPSPs and IPSPs, which is ion flow, very fast ion flow through the membrane. And it is the coordinated activity of large groups of neurons. So we're not looking at the moment.
So that brings us to the close of this panel discussion. Thank you very much for coming on this. I just wanted to do a small summary of what we discussed today. A lot of the discussions started off with looking at alpha powers of different frequency bands and wondering if alpha up or alpha down is actually very important to focus on. Is any kind of frequency band good enough? Consensus was that it's probably tapping into more cognitive control mechanisms in the brain, such as working with networks, and multiple kinds of bands might work well. Graeme was talking about the product market fit. If neurotech enthusiasts want to make startups, it might be helpful to get a good product market fit early on than trying to figure it out as you go and failing before you can actually get the product going. When we're talking about sample sizes and making stronger data sets, maybe some kind of standardization across the country would be good. That will help different researchers not keep little pockets of data, but bring it all together and help big data and help algorithms improve. Also adding a more clinical aspect to Neurotech Hamilton or NeurotechX events would be a great addition and more people who are interested in this field and help make our Neurotech developments more clinically applicable. We ended up with talking about how EEG and new upcoming low electrode placement, low number of electrodes can help develop creativity and new technologies. Thank you very much for attending this event. Give the panelists a big round of applause.